Aloha, my name is Jason Hinkle and I'm a graduate student here at the University of Hawaii in the Institute for Astronomy. Today I'm going to be talking about my recently submitted letter on the apparent relationship between the peak UV optical luminosity of a tidal disruption event and its decline rate, which is work I've been doing in collaboration with the All-Sky Automated Survey for Supernovae with the ASSASSIN team. Tidal disruption events, or TDEs, occur when tidal forces from a supermassive black hole overwhelm the self-gravity of a star and rip it apart. This results in a luminous flare that may be seen in the optical, X-ray, and UV wavebands. Properties of these flares may depend on a range of physical characteristics, including the mass, age, and composition of the star, as well as the mass and spin of the central supermassive black hole. Ground-based surveys like ZTF and ASSASSIN find many of the TDEs we study in this work, but because TDEs are so hot, we must observe them in the ultraviolet with space-based satellites like SWIFT in order to accurately fit the UV and optical emission as a black body. To be included in our sample, we require that each TDE has 3 epochs of SWIFT photometry concurrent with ground-based optical data. From here, we classified the TDEs based on how well we could constrain their peak luminosities. Here we show MCMC fits to each of our SWIFT epochs and the corresponding best fit bolometric luminosity, effective radius, and temperature. We find that the blackbody radii generally rise prior to peak, shown here in the black line, and for objects with late time SWIFT, we find that the blackbody radii continue to decline slowly at late times. Next, when looking at the blackbody temperatures, we find that some objects exhibit short timescale variations in temperature between roughly their peak luminosities and up to about 50 days after peak. Generally, though, the temperature evolution is flat, particularly at late times. Finally, for the bolometric UV optical luminosity, which we show in the top panel, we note that the TDEs appear to rise at different rates towards their peak luminosity. Another noticeable trend is that the more luminous TDEs in our sample appear to decay slower than their less luminous counterparts. Because of this, we look for trends between the peak luminosity and decay rate of our TDEs. By plotting the intrinsic scatter in this relationship as a function of time after peak, we see that this relationship is strongest at 40 days after the peak luminosity. Here we show a comparison of the log of the peak luminosity and delta L40, which we define as the difference between the log luminosity at 40 days after peak and the log of the peak luminosity. The solid squares and circles are our class A and B objects where we can accurately determine peak luminosities. Open color squares are class C sources where the peak luminosity determination is less reliable, and gray circles are the class D sources for which we do not observe peak and exclude from our fits. Finally, we note that when comparing sources that are either known to not be TDEs or sources that are unlikely to be TDEs, they do not fall on our best fit trend. As ground-based surveys like ASSASSIN, ATLAS, PanSTARRS, and ZTF continue to find more TDEs prior to their peak, we will be able to further test this trend. This is exciting because if future studies confirm this correlation, it can be used to distinguish between real TDEs and other types of transients. For more information, please see my paper linked in the description below. To see more Aloha briefs, please follow the IFA YouTube channel. Mahalo for watching.